Let us understand the energy changes during the process of solidification. When a liquid turns into a solid, the atoms arrange themselves into an ordered crystalline structure, where small ordered regions are generally referred as grains. This process releases energy because the crystalline structure is more stable. So overall, solidification is an exothermic process. The system loses energy and becomes more ordered. To understand why a material is solid or liquid at a certain temperature, we look at Gibbs free energy, denoted by capital G. The most stable phase at any temperature is the one with the lowest free energy. If we know the free energy of solid and liquid phase, then we can find out the change in free energy. And the change is usually the final minus initial value. So delta G is equals to free energy of solid phase minus free energy of liquid phase. Here subscript S and L represents solid and liquid phases. As the free energy of solid phase is less than the liquid phase, we will have negative value of delta G. Thus, negative free energy means less free energy, which means a more stable phase. We don't measure free energy directly. Instead, we calculate it from heat capacity and melting data recorded by differential scanning calorimetry, DSC. When a metal sample is heated in a DSC, it stays solid first, then melts at its melting point and becomes liquid. From the heat flow during this single heating run, we obtain the heat capacity of the solid, the enthalpy of fusion at melting, and the heat capacity of the liquid. Using the values of specific heat, we can calculate the enthalpy and entropy value of solid and liquid phases, and from this, we calculate the free energy curves for both phases. Thus here we have obtained a bird's-eye view of the experimental part. Now let us understand the free energy curves. Now if we look at the free energy curves with respect to temperature, then we can observe that, for a solid phase, the free energy curve decreases with temperature but not very sharply. As temperature increases, the solid gains entropy, but its atomic arrangement is still ordered. So the slope of the G-T curve of the solid is comparatively gentle. A liquid has higher entropy, which means atoms are more disordered. Because of this, its free energy decreases more strongly with temperature. So the G-T curve of the liquid has a steeper downward slope. At low temperatures, the solid has lower free energy than the liquid. That means the solid is more stable. As we increase temperature, the free energy of the liquid decreases faster. At one specific temperature, the two curves intersect. This temperature is the melting point, denoted by Tm. At melting point, free energy of solid is equal to free energy of liquid phase. Below melting point, the solid curve lies below the liquid curve, which means solid is stable. Above melting point, the liquid curve lies below the solid curve, which implies liquid phase becomes stable. Thus, this intersection and equivalence of free energy explains exactly why melting happens at a fixed temperature under equilibrium. As we move away from melting point, the delta G value also varies and can be seen from the graph as well. Now we know that the free energy can be written down in terms of enthalpy and entropy using the relation where G is equal to H minus Ts. This same expression can be written down for solid as well as liquid phase using the subscript S and L. Now the change in free energy is the free energy of solid minus free energy of liquid. Thus, putting equation 2 in 1, we can obtain equation number 3. This equation will give us the change in free energy denoted as delta G. Now in order to solve this expression, we will have to take the advantage of the fact that at the melting point, what happens to the free energy change? At the melting point, even though G is equal for both phases, the enthalpy and entropy are not equal. A liquid always has higher enthalpy and higher entropy. So during melting, the material absorbs a certain amount of heat. This is called the enthalpy of fusion, denoted by delta Hm. Similarly, there is a change in entropy called entropy of fusion, denoted by delta Sm. Thus, at the melting point temperature, Tm, free energy of solid is equal to free energy of liquid, which means delta G is 0. Putting delta G equals to 0 in equation 4 and rearranging the terms, we can have the equation 5, which relates change in entropy to the change in enthalpy and melting point temperature. Now putting equation 5 in equation 4, we can have equation 6 in terms of enthalpy and temperature, where delta G equals to delta Hm minus T multiplied by delta Hm divided by Tm. Here in subscript of delta H we have use m because the change in enthalpy is being obtained at the melting point temperature. Thus, by rearranging the equation 6, we can have final equation enclosed in red box, where delta G equals to delta Hm multiplied by delta T divided by melting temperature Tm. Here delta Hm, or sometimes referred as delta Hf, is known as latent heat of fusion, defined as the amount of heat required to convert the solid into a liquid at the melting point without any change in temperature. And delta T is known as supercooling or undercooling, which tells how much we are cooling below the melting temperature Tm. Thus here we have understood and derived the necessary relation relating free energy change with the enthalpy of fusion, undercooling, and melting temperature.